let me get you started on this assignment. So, on number one, what's the difference between a scalar quantity and a vector quantity? I would use the word while. I would say a scalar quantity is this, while a vector quantity is this. Okay? Just saying. Now, when you get to number 5, Diane's traveling at 70 kilometers per hour, which is 44 miles per hour, and she's going to send a text message. It takes her 1.75 seconds to type, "How are you?" How many meters will she travel? So, you have to assume that she's traveling at a constant velocity. So here's the most important conversion you're going to do. You have 70.0 kilometers per 1 hour. What you have to do is convert this into meters per second. This is the most common conversion that you're going to do. I'm going to show you exactly how I want this done. Okay? Exactly how I want this done. You're going to do this conversion again and again and again and again and again. 1 kilometer is how many meters? 1,000. Okay, if you don't believe me, look on your equation sheet. There's a conversion there. If you stop right now, what units are you going to be in? Meters per hour. What do you want? Meters per second. Now, one option is you can go hours into minutes, minutes into seconds, 60 and 60. But if you multiply 60 by 60, what do you get? 3,600. So the shortcut version is to say 1 hour is 3,600 seconds. So here's the shortcut that you can do. You can lop off a couple of zeros, and then, so the shortcut version of this conversion is that you multiply by 10, and then you divide by 36. Okay? So anytime you can convert from kilometers per hour to meters per second, multiply by 10, divide by 36. Now, we haven't talked about significant digits, but significant digits are a reflection of how good your data is. Since there's a decimal place, this has what we call 3 significant digits. When you write answers for me, you cannot go wrong with 3 significant digits. Okay? Now, when you do this conversion, so somebody do this. Take 70 times 10 and divide by 36. What'd you get, Andrew?
19.4.
Okay, when you multiply by 10 and divide by 36.
Yeah. 30. I might have skipped a couple steps.
Yeah, 19.4, right? That's it.
Yeah.
You just seemed hesitant. That's why I was like, yeah, 19.4 meters per second. Now, here's the story. There's 3 different ways that you can do this problem at this point. What I want to emphasize first of all, when you do this conversion to meters per second, don't round this to like 20. Don't round it to 19. That has 3 digits in it. You need to keep at least 3 digits in this conversion. Okay? Do not round it. Okay? Don't call it 20. You want to keep at least the same number of digits, if not 1 more. Okay? Round when you get to the end. Now, at this point, you need to figure out how far she's going to travel. I'm going to show you 3 different ways you can do this. It's personal preference. One option is that you can use distance equals velocity times time. You know the velocity, 19.4 meters per second. You know the time is, 1.75 seconds. The seconds cancel out, you get meters. So if you're a formula kind of person, Connor M. sitting there going, man, Mr. Burkamp, I love formulas. Good for you, Connor. There you go. So if you're an equations kind of person, do this. But you go, Mr. Burkamp, I was president of the Rectangle Club in high school. Can I use a rectangle? Certainly. You're going, this doesn't look anything like a rectangle. Sure it does. How would you represent her traveling at a constant velocity of 19.4 meters per second on a velocity time graph? Horizontal line at 19.4 meters per second. On a velocity time graph, that would be a horizontal line at 19.4 meters per second. What's the base of that rectangle going to be? 1.750 seconds. You have a rectangle that's 19.4 meters per second tall by 1.75 seconds. You can find the area of a rectangle using length times width. So in a weird way, distance equals velocity times time is length times width, if you have a velocity time graph. Going, oh, cool, nice. But wait, for an additional shipping and handling, there's yet a third way you can do this problem, okay? You go, Ms. Burkamp, I love ratios. You have 19.4 meters per 1 second. It's a ratio. It says this is how far I travel in 1 second. You can set it up as a ratio and go, if I travel 19.4 meters, I'm going to travel X number of meters in 1.750 seconds. Now, the beauty of this is your answer going to be bigger or smaller than 19.4? Bigger. Why? You're traveling more than 1 second. This is how far you travel in 1 second. You're going to travel more than 1 second. Your answer better be bigger than 19.4.
My bad. I got lost in the sauce. Got lost in the sauce there.
Okay. Let's throw you a lifeline. Okay. Now, when you get to number 6, I want you to have this visual. Here's a rocket sitting on the launch pad. What's the initial velocity of the rocket? 0. Sitting on the launch pad. You're going to fire the engines. The function of the engines is to create an upward acceleration. Now, I tell you that the acceleration is positive 5 meters per second squared. So, on a velocity time graph, you're going to start at 0. That's the initial velocity of the rocket. Now, an acceleration of 5 meters per second squared, which in this situation, it might be handy to think of it as that being 5 meters per second. So this velocity time graph is going to slope up like that. What's the slope of that line going to be? Do not make this difficult. Positive what?
5.
Why?
Because it's accelerating.
That's your acceleration. So the slope of this line is 5 meters per second squared, right? Now, at the end of 1 second, how fast are you going to be going? Do not make this difficult. 5 meters per second? Because that's what an acceleration means. It means for every second that goes by, your velocity is going to change 5 meters per second. At the end of 2 seconds, how fast are you going to be going?
10 meters per second.
3, you're going to be going? 15. There you go. Okay, that's what the number means. Now, here's the story. Now, you're going to do this for like 8 seconds. At the end of 8 seconds, I'm going to shut off the engines. So that's like me throwing this ball up in the air. As soon as it leaves my hand, what's the only force acting on that ball?
Gravity.
What's it going to do? Speed up or slow down as soon as you shut off the engines?
Speed up. Oh, slow down.
It's going to slow down. Is it going to keep going up?
No.
Yes.
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 It's going to keep going up, but it's going to
Until it's slow down.
slow down.
Okay.
Until it reaches the maximum height. Then what's it going to do? Stop, fall back down.
Okay.
Okay?
I'm there with you.
So on number 6, you got to do some stuff. You got to draw particle diagrams, velocity vectors like v1, and then maybe v2. Draw that bigger if you're speeding up. If you're slowing down, draw v2 smaller. Just saying. You need to draw a velocity time graph. You need to do a bunch of stuff on that velocity time graph. Questions 7, 8, 10, and 11 are all going to deal with constant velocity problems. You can work them as a ratio. You can work them as a geometry problem. You can work them as distance equals velocity times time. What you do, I care not. I'm done, you're on your own. So, do tomorrow. If you have questions, don't flip out and go, oh my God, I don't know how to do this. We'll answer your questions tomorrow. Okay, kids, we're done.
Because it's such a big one.